Hey everyone, another abstract algebra video here in which we're going to solve a very nice problem that utilizes ideas gone over in the previous two videos, dealing with kernels, homomorphisms, normal subgroups, etc, etc. Now this nice problem is taken from a graduate level text, Thomas Hungerford's Algebra. I want you to pause this video and give this problem a serious stab or two on your own, and then unpause it so that you can get the most out of this. So this problem supplies us with three givens. First off, phi is a homomorphism from G to H happens to be an abelian group, and the kernel of phi is a subset of capital N, and capital N happens to be a subgroup of capital G. With those three things on the table, we need to prove that N is a normal subgroup of G. And now here is one way we can go about doing that. First, recall that showing normality of N in G is exactly the same thing as showing that for any choice of lowercase g and lowercase n, which I'll just call G and N from now on, G and G inverse will always be a member of capital N, again for all G and G and all N and N. Now let's focus on that key player G and G inverse, and notice that for any choice of G and N, G and G inverse will always be in G due to group closure. However, now we know that phi will take G and G inverse to a corresponding element in H due to just the definition of a homomorphism. However, a homomorphism takes every element in G to a particular corresponding element in H. Furthermore, we can utilize homomorphism properties to break up phi of G and G inverse into a product of three things like so: phi G, phi N, phi G inverse. And that third term, underlined in yellow, we can utilize our inverse property from the first video to bring that inverse to the outside, so to speak. And now all three of those terms underlined in blue are elements of H. And H is abelian, so first times second times third can be written as first times third times second. And the benefit of doing that is that first times third is precisely the identity element of H. So, in other words, for any choice of G and N, phi of G and G inverse will always be equal to phi of N. And now here is the key idea that enables us to tie in kernels, that third assumption, into this proof. Recall the main idea from the previous video showing that the set of all inverse images of any H in H that phi happens to map to is given by the kernel of phi times x, where x here is just any inverse image of H. By the way, I'm using inverse image in a slightly altered sense, slightly altered definition. Please consult the previous video for those gory details. For now, phi of n and phi of g and g inverse hit the same element in H. So how about we just let x equal n, lowercase n. Then g and g inverse has to be in the kernel of phi times n. And now, so g and g inverse is lowercase k times n, where k is just some element in the kernel. Now a little right side multiplication with n inverse gives us just a simple k on the right side. And now this implies that gn, g inverse, n inverse is a member of the kernel. And now we can employ that third assumption more specifically. Kernel of phi is a subset of n, so gn, g inverse, n inverse has to be a member of n. Phrased another way, gn, g inverse, n inverse equals n prime for some n prime in n. And now a little right side multiplication once again, just by normal n. That the last two terms on the left side are the identity element, multiplied to the identity element of g, and due to closure, n prime times n is some n double prime, where n double prime is just some element in capital N, and we have proven that normality obtains. N is a normal subgroup of G.